So the next speaker and final speaker today is Jihun Park from IBS Pohang and Postec, I think. And he's going to speak about factoriality of double solids, a new version.
Okay, thank you. All right, thank you for the invitation and the introduction. I'm very happy to be here. All right, so today I will talk about this factoriality of the double solid. This is still on progress and very slow. Okay, so today, so we consider X, which is your final threefold, with only terminal CA1 singularities. Or we can consider a hypersurface of P4 with the only terminal CA1 singularities, or we can consider a cyclic curve of P3 with only same singularities. Right, so actually today we're gonna focus on the double curve of the P3 with this kind of singularity. But in this case, so our H1 of OX and the H2 of OX all vanishes. Right, so in this case, our Picard group of X is same as the second cohomology group of the this, right? And also we have this when you consider divisor class group tensor by Q, this will be a H4 and thus the fourth homology group, simply because our singularity is the isolated and the CA1 singularity. Okay. It's true. I mean, in this case, you don't have the torsion part. So that implies, so X is Q factorial if and only if. So this length of H2, I mean the cohomology, and the length of this fourth homology group are the same. I mean, are the same, then this is the equivalent condition for the factoriality of this X. All right, so this is a sort of a duality. So this duality condition, I mean, usually fails on singular varieties in general. So this failure can be quantified by the difference between these two numbers. So this number is called the defect of X, which is given by this length of H4 minus length of H2. Okay. All right, so with this notion, we can say X is Q factorial if and only if this defect is trivial. Okay. All right, and in our case, so one remark is that the on Gorenstein terminal 3/4, I mean, this Q factorial. Factorial. Known to be the same as the factorial. So no difference in this case. This is this was proven by the Kamata a long time ago. I think 88. Okay, so let me just rephrase that statement. X is the factorial. If and only if this defect is trivial. Okay. All right, so as I said, so in this talk, we're gonna focus on the double cover, so which is called the double solid. So double cover, this is the double cover. Let's say X of P3, all right, branched along a surface, let's say surface B or B is 3, and degree as let's say 2R, okay? And with the cyclic dual singularities, so AN singularities. Okay, so okay, so let me draw some picture. So here you have Pn, P3, and you have B, right? And degree as 2R. Okay. All right. And when we describe our condition says this surface has the only like a cyclic dual singularities. So let me describe singularities in this way. So A1, AM, AM. This is the number of A1 singularities, and this is up to here. This is the number of the AM singularities on surface B. Okay. All right, and this double solid can be considered as the weighted hypersurface in P1111R, right? Degree 2R here, weighted. And I will denote this weighted project space by just simply P. Okay. All right, and one more remark here. All right, under this condition, so I mean, with that condition, X, I mean, this double cover X will have only like a terminal CA1 singularities, right? Because of this condition. In fact, so B has only AN singularities, if and only if. So X has only terminal CA1 singularities.
Don't write an equation and add one more square.
Yes. All right, so these singularities on X may affect on this integral homology and cohomology. So you may have you may have some difference, positive difference because of your singularities. Okay. All right, so it's not easy to compute this defect when you have this situation. So it's not easy to compute this forced homology groups. All right, but for H2, so our X sits in this weighted project space, which is simply Toric. In this case, we have a lattice type of the theorem. So we have the same as usual. So this is the same as the Picard group of this ambient weighted project space. So that means that implies our rank of H2 X Z. This is the same as the rank of this the Picard group of the P, which is what? Right? All right, so to get this defect, we don't compute this number directly, but we're gonna compute this defect, in some mysterious way. But to do so, we need to consider like a big resolution of this X. So we're gonna consider this. So this is our X, and this is the big resolution. So I will explain what big resolution is. So big resolution. So let's say this sits in our weighted project space, and this is the blow up of this in a proper way. All right. So let me explain what this means. All right, so this big resolution is the composition of the blow-ups. So Y, this is Y naught, this is the X. And each rho I, so this, and this is the sits in the PI. Okay, so this is the blow up with the finite center. This locus of the singularity, which is the finite and non-empty. And this YK, the last part, this last part is Y, and this is a smooth. Okay, so and this Ross K, PK, I will denote by this way, P tilde. Okay. All right, you start from X in P on weighted project space. You have a finite number of the CA1 singularity. You take the blow, and upstairs, same condition, right? Finite number of singularity. You blow up, blow up, blow up. At the end, you're gonna have this smooth first time. So that's the peak resolution. Okay. All right, and I guess so. Yeah. No, no, that's different. Even like I will tell you, like this number of the exceptional divisors are different. So, for example, right, this is the number of components of the exceptional locus. The exceptional locus. So this row. Okay. So in this case, exact number. So when you describe the singularity in this way, then the exact number is given by this. So up to n and thus, right? So for surface, you have more exceptional.
Each time it goes by two.
Really? Yeah. But you're gonna have the exceptional divide, they split. Okay. All right, so oops.
The exception of the chain of singular circles.
Huh?
The exception of the chain of singular circles.
Depends on, I mean, it's alternate. So like
But in general,
no, like the last one is the conic, but I mean the cone of the, but usually like a smooth. What? No, say it again.
now you say only AN.
Yeah, AN singularities.
Then there is AN. A1, then finally.
So your local equation on the 3/4 is like this. Right? And that is this. And you take the blow, then this L like drops by 2. Yeah. By 2. So but in the surface case, you blow up, then your sectional divisor may have the split, but here you always have the cone.
Maybe after that makes it one.
Okay, we can. All right. Okay. All right. So we have Y up there, big resolution, and then we have X. So this rank of this Picard group of Y. All right. In this case, all right. So you start from the bottom. So rank of Picard group of X. Right. And you're gonna have a new exceptional divisors. I mean, new divisors, which comes from the exceptional divisors, and something else, right? Which actually, roughly speaking, comes from the non-Cartier divisor at the bottom. All right. So if you follow if you compute, and you can see this is exactly the defect, the difference between the H2 and H4. Okay. I mean, you can do it. I mean, this is not hard. But but there is a way to compute this number, this defect. All right, so this was studied by at the beginning, studied by Clemens in 83. So there is literatures for this. So Clemens in 83, he studied this case with the node, so nodal double solid. And Dimker and the sink They started this, I think, this is the 90s and then this is 2000, around the 2000s. So they consider like singularities of various types. So singularities of various types. And ROMs, this is the 2008. He considers this AD singularities. And they describe how to, this, in fact, like this paper and this paper, they describe how to compute this number, the defect in a like feasible way, the possible way. So let me introduce their way. So let me denote the number of this singularity of the yi, and in each step here, mu I. This is the number of singularities. So I is from 0 to k minus 1, right? And we consider this vector space yi, and this is the h0, and the pi. This is our ambient space here, and opi, and 2yi plus k canonical divisor. This times the ideal shift of the singularities. Okay. All right, and this delta x, this is still given by some of these numbers. Let's say j equal to 0, a minus 1, and dimension of this space, dimension of this vector space, minus and h0 and pi and opi and 2yi pi minus mu I and thus. Okay, and if you simplify this number in a like a smart way, then this number becomes this. So this is the last stage of the blow up of the ambient space, and OP and this 2y plus k like this, and this is the bottom weighted project space, and 2x and kp, and this plus mu x. Okay. All right, so we can compute this number. We can compute this number. So if we know this number, then we can compute this, right? All right, so to get this number, so we consider this blow up, and we consider this motion induced by this rho I. So I will denote by rho I bar. So this is just a simple option. So okay, so whenever you have a divisor, the value divisor, then you take the pullback and you subtract the exceptional divisor reduced. Okay, right? Then this H0. Y. AP tilde. Okay. All right, it's just the you collect the all member here, okay, which contains this singular locus for H, Y, J. This is the support J. or J up to K minus 1. Right? So, I mean, this is just simply, I mean, roughly speaking, you collect the all member here, which pass through the, whose proper transform pass through the this infinitely near singular points of this divide. I mean, this B, right? So that's the this space, and I forgot the dimension in this number. Okay. All right, so to figure out this number, you play with this, but still like it's still difficult to apply.
What we get for one node? What we get for one node?
One node means the just one node. You just collect the all. I mean, this is the in that case you just have this the same as this. So you collect the that's the dimension of the all member which pass through the other nodes. Yeah. Okay. And I can erase this. All right, this is the number of the components. And this condition can be described in this way. So this idea comes from the Ram's paper. So let's say this is the Ram's method. So whenever you have this singular point here, all right, on B, okay. So your singular point is the B in P3. Okay. All right, then B is locally looks like this. Around P. All right, because this is the AL singularities. All right, there is one. So, and he defined the condition, let's say A. All right. All right. So on H, which is here, P0, P3, and OP3, and 3R minus 4. Okay, this 3R minus 4 comes from here. So this guy degree is 2R. So this is the 4R. And this is the degree minus, I think, R plus 4, right? So when you add up, then you get this number, right? All right, and this condition, so I'll denote the P, CP0. So this is the about the this. So H pass through the P. This is one condition. And I'll define the CPJ condition. All right, so for J is between 1 and this number, L over 2 round up minus 1, right? And this is J, and this is X1J. H and P in G. All right, this parameter comes from here. Okay. All right, so this condition A consists of exactly UX linear conditions. Right? So this each singular point P, you have this many singularities. I mean, this many conditions. This is one, and this many. So, right? And what Roms proved is the following. So instead of this, he used the this. So he considered, let's say, script H. This is the H, right? Here. P3, OP3, 3R minus 4 in here. And H satisfies this condition A. Okay. All right, then what it claims is the following. So this the defect. Actually, this dimension is the same as dimension of this space. So defect is gonna be a this. Dimension of Hx minus H0, and here P3 and OP3 and 3R minus 4 minus mu x here. Okay. All right. So then when we translate, R is the so our B, and this is the degree 12. So with this theory, so what is what? 3R minus 4, I told you here. So 4R. All right, so X is factorial. Then factorial, as I said, this is the trivial defect. Okay. And thus as this condition A imposed mu x linearly independent conditions. So on this H, P3, or P3, 3R minus 4, and here.
This singularities, there is parameter L, and they behave differently when L is even and L is odd, right? When L is odd, there's something going on, but where L is even, such as A2, they even factorial, complete local ring is factorial, right? So why in this results there's no difference between even and odd L? I mean, if you only have A2L singularities, it's always factorial, right? Just because
No, it depends on the number of the singularities and the number of the positions.
But I'm talking about complete local ring.
Uh-huh.
This singularities has class group depending on parity of L.
It's true, but
In particular, some of them just are factorial even complete locally.
nope, no.
If you guys just watch it, there's one. But several.
No. All right, so okay, Let me erase this. So, all right. So let me emphasize. So here I said this this condition A consists of the mu. I mean the mu x linear conditions, but I didn't say this. They are linearly independent. All right. So if you look at this formula, then you see this delta is trivial. That means that these conditions, I mean, the mu x linearly, I mean, depend. I mean, these linear conditions are linearly independent. Okay, exactly. All right, so here is the my old widget with the Vanya, like almost like 20 years ago. So in the at that time, so we assume that the B has only A1 singularities. And the statement is the following. So number of their nodes 2r minus 1, then, and this x is the factorial. Right? All right. But if you look at this conditions, so if add is 2, I mean, you don't have this condition. It's just care about the passing through the node or not. So you may replace this at most A2 singularities. Okay. All right. So let me explain where this number come from, this r times 2r minus 1. All right, so let me give you some interesting examples. I may need this. Let me keep this. All right, so key examples. All right. So you consider this polynomial square plus WG r minus 1, 2r minus 1, and x, y, ZW, and this is U squared. This is the our double curve R. Okay. All right. So this is our surface defines the surface. I mean, if you put here 0, then this is our ramification. I mean, the French divisor on P3. All right. So and we assume that these two polynomials are general. All right. Then you're gonna have exactly r times 2r minus 1, 4 minus 1 nodes, right? Which is exactly the solution of this. Right? So r times 2r minus 1, right? All right. And this is not Q factorial because, so you consider this hyperplane section. This is a hyperplane section. H, all right? Then this have actually the two components, W, and if W is 0, then you have U squared and F squared. So that implies this, and you have R equal to 0. This is D2, and you have this decomposition. Do two. Right? All right. But the regist says this Picard group, let's say this is X, and must generate by this hyperplane section. But that means this D1 and D2 is this is even like a Q-partial. So this is not factorial. Right? Right? Let me give you, so that's why we have here like this is the optimal sort of optimal bounds. Right? Right? And let me give you another example. I have several examples which are very fun. All right. So now you consider hypersurface in P1 cross P3. And this is smooth straightforward by degree, let's say 2R. Okay. So let me give you equation. So let's say FR X Y Z W and U squared. This is the U V and this is the X Y Z W. Okay. Minus 2 HR X Y Z W U V plus GR X Y Z W and V squared. This is the equation. All right, and let's assume this three polynomials are general. Okay. All right, in this case, you have natural projection to P3 because this is the P1 plus P3. Okay, let's say this is phi. This is the projection. All right, and this projection like contract the trajectory like R cubed curves. So this R cubed comes from the others. So in P3, you have R cubed like intersection points, and that defines the R cubed curves in V. Right. So if you consider time vectorization, so P3, and here this is our field, and so then this is the contraction of this this CI, this R cubed the CI, okay, and this will be a 2-to-1 map, finite cover, right? And this ramification diverger given by the discriminant of this equation, right? So this is defined by HR squared minus plus FR and GR equal to 0, right? And you see this this guy contracted this R cubed curves to R cubed node. Right. So this is our this is the double solid that I want to consider, and you have small contraction to X from smooth one. So that means this is not Q factorial. Right? Right? All right, so and so far nodal example. So let me increase the singularities. All right, let me slightly change this equation. All right, so here I will consider polynomial in x, y, z, and here instead of w, I will use here r, okay, times uv, okay, and here, thus. Okay. All right, and this 8 GR or general, okay, and here you have this W, right? Everything's fine, right? And instead you have this, okay? Huh? Yeah, special, sort of special. Even like now our B, right? Let me our ramification division B here. Let me discard. So this is okay. This is what? This is okay. W to the R to R and F R X Y Z times G R X Y Z equal to 0, right? So this guy has how many? R squared and A not A1, and this is A to R minus 1 singularities. What? Correct? Correct. All right, and this, by the same reason, this is not Q factorial, right? All right, but there is another way to see why this is not Q factorial. All right, let's say from the viewpoint once. I mean, this condition. All right, so we have a 2r minus 1 singularities. All right, so this number 2r minus 1, 2 minus 1, this is exactly r minus 1. Right? All right, so that means each singular point, you have this condition, P, CP, r minus 1 condition. Here, shift. Right? So that means right? This condition. Right? So this is about this type of the polynomials. So right? This condition cares about this, only cares about this type of the polynomials. Right? And this condition means, and this, if you have this type of polynomial, then this is vanished. Right? So this is the condition on exactly H0 and P2 and OP2 and 2R minus 3. Right? H. What is this small? This is the like just the some polynomial. Some polynomial like this condition cares about this type of the polynomials. I mean the arbitrary polynomial of degree 2r minus 3 in this variable, right? I mean, without this, it's automatically vanished, right? Only like because you take this condition. All right, and then so you have this R square condition about this here, all right? All right, but you see, we are here. Your point P is here, right? In P2, right? This is actually the this plane, right? And this FR, let's say this. Let me use this. Right. So your FR, our singular points are here, right? And let's say this FR, this is let's say Z1, this is the in P2, and this is I'm talking about this hyperplane, and you have this Z2, right? This is P2 here, right? So and this intersection is exactly how many points? R square points, right? And this H0 P2 and P2, and this is exactly this is 2r minus 3 is the R plus R, degree of Z1 plus degree of Z2 minus 3. So this points impose the linearly dependent condition. This is impose linearly dependent condition. This is by Taylor. Right? So that means your defect is positive. Okay. And I have 5 minutes, so let me give you one more example and then give you. Okay. Finish. All right. So. All right. So. Now I consider like this type of the double solid. So this is the ramification divisor. So we consider double solid ramify along this surface. Or okay. All right, and let's say this is general. Okay. All right, then by the same argument in the first example, you take the hyperplane section by x equal to 0. Then you have the two components for the divisor. So that means that these components are non-Q Cartier, right? So this is not Q factorial, right? And if you look at the singularities here, so you have exactly so this is the x equal to 0, and this is w equal to 0, and this is HR 2r minus 1, 0. So you have exactly 2r minus 1 singular points, and which is the a 2r minus 1 singularities. Right? All right. Then at this moment, I made a wild conjecture. Okay. Well, I'm not sure whether this is correct, but we conjecture. So following. So if the all conditions are same, so X is the double solid of P3 ramified branched along the surface B, which has the AN singularities only. If the number of singular points is strictly less than 2r minus 1, then X is factorial. So I just use no. What do you mean? CA1 singularities only.
A1, but.
4 minus 1. Yeah. Not here. So X only has the CA1 singularities. That's the assumption. Yeah. So I checked for this is nothing to prove. It's no singular points. So, and this is about the 2 points, 2 singular points, and then still I don't have proof for the with this condition, but this R is the degree, 2R is the degree of the so if R is 2, then it's about 2 points. And X is 2R minus this is 3. So about 2 points. So if I have extra condition, so at most the singularities, the singularity of B is the at most A4, then it's true. 3. This is about the 5, and with this condition, it's true. But without this condition, I don't know. For example, like this R equal to 2 is about the quartic surface. So you may have this A19 singularities. I don't know. So this is still progress. So in a very slow way, because I didn't pay attention too much. Whenever I have this kind of talk, I spend 2 or 3 weeks. So that's why. Sorry about that. So next time, hopefully I can make a big progress. Thank you. This.
I think at some point I wrote a quartic with CA 10 or 9. 1.
I made a mistake. Sorry.
We have to check, yeah.
What?
I think it was not 2 factor.
If one singular with the what?
We can check.
Okay. Well, and this it says this H2. H4.
Can I ask a horrible question? So the weekend that you missed, you learned about resolution of singularities with weighted blowups. So these are easy to resolve with one weighted blow up, right? Depending on R being, depending on L being even or odd.
I mean,
Resolve, but you get the stack, right? But then the point is, but now there is another talk on Thursday talking about how to compute Chow rings over stacks, and these are toric, so they're not so bad. Maybe there is a different formulation of this.
maybe, but I mean, it's
Yeah, so but they are not well formed, so you have to be very careful with computation. So, for example, the way you would resolve this, you would get P L L L L L L 1 or 2L 2L 2L.
well, here everything is combinatorial and it's very touchable.
Yeah, so that should be combinatorial too, because they're all weighted projective stacks.
I mean, for the explicit examples.
Maybe this is for better for G-types.
Yeah, sure. Yeah, the resolution here is stupid. Yeah, they're stupid. They're all like 2, 2, 2, 2 or something. Yeah, I agree.
In that case, you may have some problem with this divisor class group and then G4. I mean, if you have this D type or E type.
Young people.
You have a single conjecture for just hypersurface.
Maybe, I mean, for some, but I haven't thought about it like seriously. I mean, it might be possible because it's Ram's formula is about the AD type singularities, and he cares about the also like hypersurfaces. So.
Any other questions? Okay, then let's thank the speaker again.